Hello everybody. In this video today we're going to have a look at colors in C and SDL, how they work and how we can transform them to create really nice animations in the end. Now I already just wasted 2 hours recording something and then I noticed that my microphone was turned off. Oh my god. And now here I am again. This is my second try. So let's create a new project in the projects directory called, I don't know, the last directory was called Rainbow. And we already coded some stuff here. I will create a new directory that is called Rainbow Colors, just to distinguish it. But maybe this is a big advantage because now I don't have to struggle so much because some things are already clear and I can explain some things better to you. As always, this is not a tutorial, this is a live coding session, and I hope this time it works out. So what I'm doing is I'm creating a C file and I include standard.io, SDL2 and math.h because we're going to need to do some mathematics here. You will see later for what exactly we will need that. And then let's quickly set up SDL. Without too much explanation, we're going to set up the video subsystem because we're generating video on the screen. Animations, we're going to create a window on the screen. So we need the video subsystem, then we're going to create a window. SDL create window. And the window has a title, Rainbow. And then what we do is we specify the X and Y position. We just position the window at the center of the screen. Using the SDL window pause centered flag, then we provide a width and a height. And some flags at the end. I'll use 0 because we don't need anything. The flags are specifying things such as borderless windows and stuff like that. We don't need that. The width of my screen or of my window is going to be 900. The height is going to be 600. And aside from that, what we need is something to draw on. What this thing right now does is, let me just show you, just so you know what I'm doing. Right now we should have a window on our screen. Let's go to the subdirectory Rainbow Colors and let's compile this software. We need a compilation command for that because we're using SDL2, so we need to use the right compilation flags to link the libraries correctly. So let me just paste this from the installation guide, and of course it doesn't work because here I referenced the wrong source file and I have to compile rainbow.c. So let's see, it does nothing. Why does it do nothing? We've created a window and then we wait for 3 seconds. So I actually, of course it does nothing because I just compiled the software. My brain is already molten, guys. I have to, of course, execute the software. And there it is. This is our black window called Rainbow. As a next step, we take the window, SDL window, right here and store it in a window variable, and then what we do is we want to draw something on this black surface of the window, so we get this surface of the window, as the name already says, surface, and we store it in a variable and get it from the window using get window surface. There it is, and we provide the window to extract the surface from. And then we can draw something on the surface. Right now, just let me show you. the screen is of course still black because we don't do anything with that set surface. What we want to do now is we want to draw something. So let's call the fillRect function, which fills a rectangle on the surface, on P surface. Then we provide a pointer to a rectangle and a color, and that color is going to be white for now. FF, 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 FF. And that's it. Of course, we need to create the rectangle as well. Rect, and that is an SDL rectangle, and we initialize it at a specific coordinate 50, 50, and it has a width of 100 and a height of 100 as well. And now we don't yet see a rectangle. Let me show you. It's still all black. And that's because we need to update the screen surface. We need to tell the software that we are done manipulating the video memory, and now we can update the window surface, P window. And let's try again. And there it is. This is our small little rectangle. All right. Now, the application always runs for 3 seconds and then terminates itself. Of course, we don't want that. We want to keep it alive for as long as we need it, and then we want to be able to close it. Just let me show you. During those 3 seconds, I can't click the close button. It closes itself. Well, I can click the close button. The application just doesn't react to it. So what we have to do now here is create a so-called event loop, and this is also documented on SDL, on SDL's documentation under poll event. What we do here is we create a loop that checks if the game is still running or if our animation is still running. And while it's running, we're checking for events. And events are things such as mouse events, keyboard events, quit events. So let's just copy that, paste it here. While the game is still running, let's create a variable, game is still running, and it is running, so we set it to 1. And then we poll all events that are handled, and then decide what to do with the events. So here we have now set the event flag, and here we can check the event type, and if it's an SDL quit event, then we obviously set game is still running to false. Simple, right? So, and while the application is running, let me just indent that. Oops, that's the wrong indentation direction. While the game is running, we also delay the frames a bit, just so that the application has some time and doesn't recompute everything as fast as it can. So as you can see, this application is still there, but now it stays alive, and when we press the quit button, it quits. Awesome, right? Okay, now this is the base. This is the basic frame, the basic blueprint for an SDL application. From this point on, you can do everything yourself. You can technically even create your own 3D engine. You can create your own game engine. You can create your own Google Earth. You can create your own, navigation system. You can create your own graphical user interface using completely customized logic. And that is because everything or all the graphics that you generate are basically individual pixels set to individual colors. Yeah, and what we do here is we create a rectangle and fill it white. However, you can also create a rectangle with a width and a height of 1 and then fill it at a specific color which you compute, and then you can generate whatever application you want. So this is the basic blueprint. So we can also, so let's create in this loop a new function. Let's call it animate, and we provide this function the p window and the p surface, because those are the things that we're animating. And then I will copy all, or I will cut all the rectangle creation logic out of this main method and create a new method, animate. It will accept an SDL window, p window, and an SDL surface, p surface. And then in here, no, that's the game loop. In here, we paste the rectangle which we create on the surface, and that's actually already it. Let's see if the application still compiles. It still compiles, but we don't have a rectangle. Why is that? That is because we are calling the method here. Then we are filling the rectangle here. Of course. And then we have to update the window surface, of course, in the loop after we animate. Before that change, we only updated the window surface once. And there it is again. So what can we now do? What we now have set up is a loop which generates pictures over and over again. So we can technically, for example, introduce a variable int counter that is 0, and we can do something like this. We can just add the counter on top of the width of the rectangle, and then also increment it after each call, and then we get the following. We get a growing rectangle. We can also update the position of the rectangle depending on the time that has passed, but depending on the counter. So let's do that. And this is now quite interesting. The rectangle is moving down and it's expanding in width, but because the previous rectangles are not deleted from the windows or from the surface's memory, they are still displayed. So we are generating new rectangles, but the old ones persist. And that's what causes this triangular animation. To delete the old rectangles, we can simply do the following. This is a pretty simple hack. We can call fill rectangle p surface, and then we call null as the rectangle, and then we provide the color black. I think this should work. Let's see. Yeah, and as you can see now, the rectangle is moving down and it's expanding. And because we are now deleting all the memory here, because we're providing a null pointer as the rectangle, we see just the rectangle and its expansion. Alrighty. We could technically also fill a rectangle we could delete the entire screen using a rectangle that is black, that is the entire size of the application. So we could construct a rectangle that is 900 pixels wide and 600 pixels high, and that is black, and then we could just fill that rectangle. That's also possible, and I've done that in all my other videos. But this is something nice that one of you commented in the comments under a video, and now I'm following that advice. All right, now we want to have a look at colors in this video, as I said in the beginning. Right now we are simply animating a rectangle. Now, how can we modify colors? For example, a color in SDL is a UN32. It's a 32-bit color. And right now we're using something like this. And providing the rectangle a color. That color is white because all of the color fields are maxed out. If I reduce the value and set it to 0 of one of the fields, then we get a different color. As you can see here, now it's pink. And if I reduce another field, we get a different color again. Now it's, oh, how is it pronounced? It's turquoise, cyan, it's these colors. All right, that's how colors are generated, and the downside of SDL is that it's very low level and it accepts only RGB colors. That means we have to set this color array or this color integer here. There is a method, well, all the colors in SDL are RGB. That is because the pixels on your screen, the small pixels on your screen, they are composed of 3 lamps, and they are red, green, and blue. Let me just look that up for you. RGB, Wiki, English. Yeah, so all the pixels are red, green, and blue, and depending on which color you pick, or depending on how much you turn on an individual light of a color, the colors mix, and depending on their proportion, you get a specific colors. For example, if you turn on red at 50% and blue at 50%, you get this pink. If you turn on green at 50% and red at 50%, you get yellow if blue is 0. Yeah? So you always have to generate those combinations of colors. And this causes the following issue. If you have, or at least this causes an issue if you want to do what we want to do in this video. We have now basically three boxes of colors: red, green, and blue. Maybe this blue. And they are combined somehow. Let's do it like this. And then you get a resulting color. Maybe this one. The issue is that there's no nice way to combine those colors in a way that they transition nicely into each other. So how would you set, well, how would you set, for example, if red is 255 right now, oh God, 255, green is 0, and blue is 255, then the resulting color would be a mix of full red and full blue, which would be this. Okay, I don't know if this makes perfect sense right now, but this would be some RGB color defined here. But what would be the next color in the rainbow? And for this, you would have to do some advanced calculation that is very hard, because if you increment red, then it will turn from 255 to 0 because it's overflowing. 255 is the maximum value in a single byte. And the same is the case for blue. And if you increment green, then you will only add a tint of green to the color, which might not be what you need for smooth transitioning through the color space. So basically, let me just open that up. I found this graphic earlier, which basically describes how RGB colors work, and they are forming a three-dimensional color space. You have values of blue from 0 to 255, or at least in computer engineering, in computer science, it's 255 because it's usually a byte, but in mathematics you use 0 for complete darkness and 1 for complete brightness of that color. Then 0 to 1 for red and 0 to 1 for green, and you have a 3-dimensional space formed naturally from that. If any of those colors, of those subcolors overflows, you reset that individual color and you can't really form a smooth transition between colors. Let me show you how that looks like. Let's do the following. We will, in Animate, loop over each individual pixel for int x equals 0, x smaller than width, x is incremented here. And then let's do the same for int y equals 0, y smaller than height, y plus plus. So we loop over the entire screen, and x and y make up the coordinate that we're on the screen right now. And for each coordinate, we create a single pixel rectangle we only need to reset the screen once, so we extract this command up here. So for each pixel, we create a single pixel rectangle at the coordinate x, y, x, y. Then width and height of the rectangle are 1 because we just want to draw a single pixel. Let's make the color white just for this experiment, just for a second, just for demonstration. If I execute this now, we get a completely white screen because we are looping over every individual pixel and every color is set to white. Now, what if we start with an initial color that is 0? And we set that color in fill rectangle here at the end of this, and then increment that color. That means we want to smoothly transition colors. Okay? Then what happens is something like this. We increment colors and we see many, many resets in the subspaces of the color. Yeah, and that is because of this cube-like, well, characteristic of the RGB color space. Now, what we want to do is we want to create a smooth rainbow over the entire screen. And for that, RGB is quite hard to use. We could use an SDL method that is called map RGB. And let me just pull up the documentation for map RGB. And what map RGB? There it is. So map RGB takes as input the R value, the G value, and the B value, and a pixel format that is a property of the window. We can just extract it from the window and then put it in here. It's defining how each pixel is, or how each uint32 is storing the data for a specific color. But it is not very important for this video. What matters is we pass in R, G, and B individually here, and then we get the uint32 as a response. And what we could do is we could increment one of those and see what happens. Because then different parts of the 32-bit number would be incremented. Let me just show you in Paint. If we have a... Can I make this bigger somehow? Image bigger. I want to have a 9000 by 6000 image. Okay, and I will zoom into this subspace here. So let's say this is the number 0x000000. I will just use 3 bytes for now. It's normally 4 bytes, but it gets the point across. So this is R, this is B, and this is G. Oh god, RGB, I mean. RG, and this is B. Now we can, instead of incrementing the whole number, which we did before, we can increment the individual properties of this color and see what happens. So what we can do now is we say, we first need this format. We can get it from the window, I think from the window. Let me just open the documentation again, just to ensure I'm not telling you anything that's wrong. So where's the window definition? Here. And the window somewhere has a pixel format, as far as I remember. Yeah, there it is. There's the format, but this is not the window. Wait. SDL window pixel format. This is a method to get the pixel format, but we're looking not for an uint32 that describes or that identifies the format, but we're looking for a pointer to the actual pixel format that is in use. To do that, we can access it on the window. But where is it? SDL window. Well, anyways, it's not important for the video. It's a property. I'm very sure it's a property of the P window. So let's extract the SDL pixel format, which is a pointer to a format. So it's a P format, and that is coming from P window and an arrow on the format property. And that should compile. Let me just, no, it doesn't compile because what did I mess up? I forgot a semicolon somewhere. No, of course, I didn't complete that method down here. Here we provide the P format as input, and then we provide the RGB values. Yeah, and RGB they are uint8, so they are a single byte. And let's say R is, yeah, let's make them all 0 for now. RG is 0, and then B is 0 as well. We could define them out here. And then we map the RGBs, and then let's increment all the individual subfields. Let's see if that causes a smooth transition. Of course it doesn't, because dereferencing pointer to incomplete type SDL window is was I wrong? P window format. Maybe I was wrong. Where is the pixel format coming from? SDL pixel format, maybe Windows Surface. An SDL pixel format describes the format of the pixel data stored at the pixels field of an SDL surface. Okay, is it part of the surface? Oh, it's part of the surface. Okay. All right, so we have to access the P surface up here. Oops. P surface. And that is working. And as you can see, this is very similar to the pattern that we had before. It's actually quite too similar for my taste. What if we increment just 2 of those? Let's see what happens. Still looks the same. What if we increment just 1? Maybe just the blue one? Why does it always look the same? Ah, it's because we don't even use the RGB color here. Great. So of course we want to use the UN32 color that is generated in here, not the one up there. And then we don't want to increment the color here. Okay, now we should have a different result. Yeah, so now we are incrementing only the blue color, but as you can see, you always see these resets of the color. So how do we smooth transition between colors? And that's where our color spaces come in play. Yeah, and that's what happens when we transition multiple colors at once. We could do something like divide this by 2 and then do whatever modulo 10, whatever, to play around with it. But it won't really change how the colors fade into each other. There needs to be some deeper truth here that is to be uncovered. And that is, we want to use not this cubical RGB color space where colors reset all the time, but we want to use a spherical, a cyclical color space. And that is HSL or HSV, which stands for not RGB, red, green, blue, but it stands for hue, saturation, and lightness. And the hue is basically the color that you pick. So you start with a color on the left hand of the spectrum, which is associated with 0 degrees, and then you walk around this spherical volume, the cylinder, and transition through the colors smoothly, as you can see here. So there's this smooth rainbow-like relationship between the colors, and that's what we want. And as soon as you hit 360 degrees, you can just transition to 0 again, and it will be the same color. So as you can see, the color wraps around this spectrum. And yeah, the lightness, the L value, this is a value from 0 to 1. And it determines how bright the color is. Well, it's the lightness. So it starts from black and then gets brighter or lighter and lighter and lighter until it's white. That's why the bottom border is black and the top border is white. And all of that is for saturation 1. If you reduce the saturation to 0.5 or 0, then you will transition into grayscale. So saturation 0 would be gray colors only. Well, gray is gray a color? I don't think it is. Yeah, as you can see on this image here we have a fixed hue, it seems. And no, I don't really know how this works right now. Basically, this is a nice graphic. So here you can see the H value, the hue, as walking around this circle of colors. Quite nice. But now comes the big downside. SDL and many other low-level graphics libraries don't support HSL colors. They only support RGB. So how the hell do we know? How the hell do we get HSL from RGB. No, the other way around. We want to work with HSL only, but input RGB to SDL. So how do we solve that? There's quite some math happening there. Let me just show you. We can find the solution on Wikipedia, where we look up the HSL color space right here. So this is the documentation, or not the documentation, this is all the knowledge about HSL and HSV that you need. And somewhere down here, yeah, there's the principles. If you're interested in color theory, then have a look at those things. It's quite interesting. Maybe I'll spend more time here. But just for the sake of this video, all we need to do is we want to convert HSL into RGB. And this is listed somewhere down here. There it is. Color conversion formulae. Okay, so what we need to do, looking just at the code, is we don't want to use an RGB color. We want to have a color. It can still be UNT32 that is SDL compatible. And it can be RGB. So let's feed that into here as well and call it RGB. But we want to input, from our perspective, only HSL. So let's do HSL. Let's create a method RGB from HSL. And we input into this method right here, into the HSL method, the H value, the S value, and the L value. And that's basically the interface we need. We say that we want to work with HSL, and we now magically somehow define this method where we don't know yet how it works. And this method, this interface, will return RGB magically. And how that magic is done, we will find out now. So let's do that. Let's create a method that returns UNT32 and let's call it so UNT32, and the method is called RGB from HSL, and we feed it the values double H, because it can be a number between 0 and 360, but it can also be a floating point value. It can be 50.75, for example. We don't want to limit it to just integers for now. Then we accept a saturation. The saturation is a value between 0 and 1, so it must also be a double. And then we accept the lightness, which is also a value between 0 and 1. And now how do we convert that stuff? So to convert from HSL or HSV to RGB, we essentially invert the steps listed above. Okay, we don't know the steps listed above, but this is important. RGB are values between 0 and 1. So basically 0 is light is turned off, 1 is the light is turned on. And that is important for our calculation. First, we compute chroma by multiplying saturation by the maximum chroma for a given lightness or value. We don't need to know what that means right now. Next, we find the point on one of the bottom 3 faces of the RGB cube. Yeah, so here it also references the RGB cube, which has the same hue and chroma as our color. Finally, we add equal amounts of RGB to reach the proper lightness or value. Okay, but here's the formula. Given a color with hue H element 0 to 360, saturation S element 0 to 1 and lightness L element 0 to 1, we first find chroma. As far as I know, the chroma is a number that represents how far a value is away from gray. And this depends, of course, on the saturation. So how saturated is a color, how colorful is it, and how bright it is. Yeah, and so basically we can just write this formula down. C equals 1 minus 2L minus 1. This is absolute here. This is an absolute multiplied by saturation. So let's do that. Double C equals, I have to look this up quite frequently now, 1 minus absolute 2L minus 1. 1 minus absolute 2 multiplied by L minus 1. And all of that multiplied with the saturation. So we just pick the formula here from the Wikipedia article, and we don't bother with it at all for now. Then we can find a point RGB R1, G1, B1 along the bottom 3 faces of the RGB cube. So the bottom faces of the RGB cube. I don't know, so it must be some border here. I don't know. And we calculate for those RGB1 values intermediate values. H dash equals H divided by 60 degrees. So let's just take this over. Double H dash equals H divided by 60. And then X equals C multiplied by 1 minus H dash modulo 2 minus 1. C multiplied by 1 minus, okay, X is equal to C multiplied by 1 minus absolute H dash modulo 2, H dash modulo 2. Now this won't work, but we will see in a second. Minus 1, minus 1. Then let's close all the parentheses. And that's it. And if I compile that, it won't compile, but this is not yet the error I was, oh, it is. Up here you can see invalid operands to binary modulo. Let me just scroll up so you can see the message here. Invalid operands to binary modulo have double and int. Yeah, and the problem is here that you can't use modulo on a double. That is because modulo is a simple integer operation. Yeah. And as this text here says, in the above equation, the notation H dash modulo 2 refers to the remainder of the Euclidean division of H by 2. And that is the modulo. It's the division with remainder. And here this article says it's the process of dividing one integer by another. So it's not mathematically defined for floating point numbers, or maybe it is, I don't know. But traditionally it's for integers. And what we have to do is we have to use a modulo operation for floating point numbers. So what we do is we call fmod of hd of h dash, which is the same thing as modulo, it just accepts floating point numbers as input. So if you, for example, calculate 10.1 modulo 2, then the result is 5, and the rest, which the modulo computes, is 0.1. 10.1 modulo 2 is 5, The rest is 0.1. All right. So let's just compile that and see what happens. We have an issue somewhere. A semicolon is missing here. But now it should compile. No, it doesn't compile. HSL. Yeah, of course, we haven't really completed the code. We first have to feed values here into the HSL thing. But we haven't really even completed the conversion here, so let's just do that first. So we have now set up x and h dash down here, x and h dash. And now here's the formula, the main formula for computing RG and B1. So basically R1 is C and G1 is X and B1 is 0. If H dash is between 0 and 1. If you have no idea about color theory and all those color codings, then you probably have no idea what this means. But I mean, as a programmer, you can just do the following. You just read this thing. If H dash is between 0 and 1, and then you write it down. If H dash is bigger than 0, and H dash is bigger than 1, and then something happens inside this if clause. Then, in this case, RGB1 are C, X, and 0. So we need to create variables that are double R1, G1, and B1. And here, R1 is equal to C, R1 is equal to C, G1 is equal to X, and B1 is equal to 0. Now, don't bother with what's going on, just continue writing down the formula. If HD is now bigger than 1, and no, wait, I messed up this if clause. If HD is bigger than 0 and HD is smaller than 1. Well, I'm lucky that I just caught this. I wouldn't have figured this out so fast. Now, if HD is bigger than 1 and smaller than 2, then we do the following. X, C0. X, C, and 0. And by the way, we have to refine the if statement. We have to say HD is bigger than or equal to 0. And the same for this if clause, of course, because the formula here says if 0 smaller or equal than HD. Now let's continue with the third statement. Here we have 0CX. So let's just copy all of that, increase the boundaries, and then let's input 0CX. Then let's copy all of that, increase the boundaries. Yeah, the boundaries here are 2 and 3, and then the next boundaries are 3 and 4. As you see here, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Okay, the next boundaries are 0xc, 0xc. The next boundaries are x0c, x0c. So let me just try to not forget that. x0c. And then I think it's the last one. I think it's the last one. By the way, if you're wondering how I'm incrementing those numbers, just like this, it's a command in Vim that's very very nice for incrementing. You can also decrement, so you don't have to type the numbers all the time if you just need increments and decrements. It's Control A for incrementing and Control X for decrementing in Vim. So in case you're using Vim motions in Visual Studio, or if you're using plain Vim like me, then that's what you need. So, and the last statement here is, or the last association is C0x. C0 and X. And then we have calculated the values R1, G1, and B1. And finally, we can find RGB by adding the same amount to each component to match lightness. Yeah, so here you see we have these R1, G1, and B1 values, and they are base values. That's why they subscripted it with the 1. And by adding a fixed value on top of those, basically we add brightness, because we add the same value on each of those. So no color dominates. All colors increase at the same rate, and that's why they get brighter instead of shifting the color. And that constant is called M. And M is L minus C divided by 2. So let's create that constant. M is L minus C divided by 2. Very, very simple. We don't have to bother with what's happening here. And then we return, or we have an RGB value. And as you saw earlier, we can use the map RGB function. Map RGB function in SDL, we can provide the P format here, then R1 plus M, G1 plus M, and B1 plus M, and those are our RGB values, and they will return, or they will now generate a uint32. And the P format, the pointer to the format object, is not available here, and that's because we need to pass it SDL pixel format. So basically this method now determines, given a pixel format, P format, and given HSL, what is the RGB, the corresponding RGB pixel value. And well, it's not too much math, we just have to accept what's on Wikipedia. So let's see if our program compiles. No, it doesn't. Too few arguments. Yeah, we have to, of course, provide all the arguments now to the function. So here we have to say in RGB from HSL, we have to pass P format as input. And I think that's almost it. We just have to now specify what our H, S, and L values are. So double H, let's say, is 50. H is the hue. Yeah, okay, so to remember, let's have a look at this image right here. H at 50 would be between 0 and 120 degrees. That would be, I think, yellow. And S is the saturation. We want full saturation, full colors. So we set it to 100%. And then we set the lightness to 0.5. Because if we set it to 100%, then we will have the L value 1. And that is this white border here, which will result in a completely white screen with no distinguishable colors. And 0.5 is exactly this middle line here where the colors are most full. Okay, then let's see, can we compile? No, L is undeclared. That is because I have entered a capital L here. L, it's a lowercase l, of course. Let's try to compile, and it's still doesn't work, and that is because I have an undefined reference to symbol fmod, and that is because I haven't linked the math library. I have to attach the command link lm, which links the math library, which we embed up here. All right, let's try. Oh. -lm. And there we go. It's a black screen. Why is it a black screen? Okay, what are we doing wrong? Something somewhere must be wrong. And I know what's going wrong. In this method here, map RGB, where is it? Let me just close all of those open tabs here. Map RGB in SDL2 expects as input the pixel format and then the R, G, and B color values, but they are expected as uint8. And here, as the documentation says, it's the pixel value in the range 0 to 255. So 0 is still completely turned off and 255 is now completely turned on instead of 1. And in the mathematic article that we have read, I have now accidentally closed it. Let me just open it again. Here, this says mathematically RGB are element 0 to 1. So they have values that are between 0 and 1. In computer science, 0 and 1, if you represent them in a single byte, which is 8 bits, then you get values between 0 and 255. So if you want to max out a single byte and what it can represent, it's 0 to 255. So what we have to do is we have to multiply those numbers. And I would say we should probably create a new variable that is the final R value, that is R1 plus M, which is a value between 0 and 1, not mathematically, because we use the doubles. And then we multiply that with 255. And then let's do the same for G, R1, G1, and B, B1. RGB, yes, correct. And then let's pass those here, RGB, and see if that works. And I have messed up because I have just set the type as uint instead of uint8. Okay, let's try again. And this looks very, very good. We now have a yellow surface just as we have estimated in the beginning. So it's always quite clever to think what your code will do and only then execute it. And here we stated that we want to have a yellow screen. And now let's make up a different color. Let's say we want to have a blue color. That would be 240 degrees. If we can get 240 to result in blue, then we are good to go, I would say. And it's blue. It's a perfect pitch blue. Pitch blue? Do you even say pitch blue or just pitch black? I have no idea. So now I would say we can properly convert colors between HSL and RGB. And what we now can do is we can technically, or should be able to generate some rainbow transition, because all we have to do now is to increment the H value. And this will look horrible probably now if I just increment it here in the code directly. And it's just black. Yes, that doesn't work. Why doesn't it work? It doesn't work because we probably have to modulo it. So H or F mod, and we have to ensure it's not growing too much and it's not going beyond 360 degrees. Let's see if that works. Yeah. And here we have now color transitions, rainbow colors on a very, very narrow, almost eye-hurting scale. That doesn't work. Because now for every individual pixel, I'm incrementing the hue. That might not be what we want. We want something else. We want something else. I want the following. I want to have a two-dimensional plot of maybe whatever, anything actually, and the values, the values are represented by the colors of the rainbow. And we can do that. We can do that by, or I think we can do that. I haven't done that. Didn't get that far before. I would say we should create an H value, a hue value, and that is something two-dimensional. What if I do Fmod so it doesn't grow too large, and then I do X multiplied by Y, and then the maximum value is 360. After that it will wrap around. Ooh. You can probably spot the moiré effect right now. That's a nice pattern. That's a really interesting pattern. If I move that on the screen, oh, that's crazy. What happens if I do sine X multiplied by Y? This will probably be black. No, it's not black. I don't know why, but I expected it to be black because this will result in a hue between 0 and 1, because sinus wave has a maximum value of 0, of 1 actually. So this sine wave, maybe we should take the absolute of the sine wave and then multiply it with 360. And let's see how that looks like. Oh no, oh no, oh no. Wait. Why is it red now? It's just red. Ah, it's red because the value at 0, the hue value 0 is red, of course, and sine is red. But I multiplied with 360 before. Ah, and 360 is also red. Maybe that is the reason. But the values between those shouldn't be red. Okay, what? Maybe the frequency of that sine wave is way too fast. What if I do 0.01 multiplied by this, and then let's see. It's still red. What if I remove the absolute? Is that a problem somehow? Okay. This is another interesting pattern here. So what does this plane sine wave look like? It looks like this. So X multiplied by Y is not really good, because at the end of the screen, I'm going to multiply the entire width of the screen plus the multiplied with the height of the screen, which is 600 by 900, which is probably way too large colors. This is not a good idea. what if I do sine x multiplied by sine y? Okay, this is a small chess pattern. Let's say chess grid. Or a checkered pattern. Yeah, okay. What if I modify the amplitude by saying that the sine wave should be moved 180 units up and the amplitude should be increased by 360? This looks like it uses the full color space. Now, okay, let's derive new coordinates here. And they are doubles. Double x scene, or let's call it xs. And xs is double x. Oh no, we can even do it like this. We can just use doubles directly in the loop. There's no need for integers here. And then we can divide that by something large. And this should give us some more visual pattern. Oh, what's that? This doesn't look correct at all. It looks funny, but what? No, I haven't expected that, honestly. So I think something is wrong with the code. But what is it? There are really weird wraparounds in this. So what's happening in here? Double x, x is being incremented all the time. At some point we should have a derived x, a scene x scene, that is x but modulo. So let's use f mod here. Modulo 360, I think. And then y scene is f modulo of y, blah, blah, blah. And then let's use x scene here and y scene here. So what I'm doing is I'm transforming the coordinates into something new that can't overflow. And it looks even weirder. Oh my god. Ah no, it's valid. I thought this modulo was wrong, but it is not. It's not, I think. Wait, so what if I set the hue just to 160? Does it result in a reasonable color? I'm just doubting my algorithm a bit. 160 is just this color, yeah. And 120 should result in green. Yeah, so all of that is working. So what's the issue? The rectangle is placed at x, y, 1, 1, which is a single pixel, and then we fill that pixel with the RGB value that we generated from HSL on that surface. What is some stupid simple test that I can do? Maybe, let's say h is 120 if the absolute value of x squared, if I want to generate a circle that is of different color. If power x to the power of 2 minus power y, wait, what am I doing? How do I compute the distance? It's x to the power of 2 plus y to the power of 2. Then, and of course, if that is bigger than, let's say, 500, then what do? Then h is 30. Oh no, let's make it 0. Then it's red. Yeah, okay, so we have a small circle of a color, and outside that circle it's red. What if I don't use the power operator? So somehow the HSL looks correct, but I can't really figure out what those bugs that we observed earlier were. Yeah, so here we have a straight line because we are looking at a linear relationship between x and y. What is the issue that we saw earlier? I think I know. Math C sinus. I think the sinus function is not what we want to use. No, the sinus function accepts an angle in radians to find the sine of. It accepts an angle in radians. That means from 0 to 2 pi. It can't be that hard to make some smooth transition. Sinus x and x, okay, the first couple pixels are 0, 1, 2, 3, 4, 5. What is 2 pi? 2 pi is roughly 6. It's between 6 and 7, so depending on how the C compiler or the runtime, I don't know how it's working. At 7, the sinus wave should already reset. So we should see some repeating pattern after 7 pixels. And I think that is the case. So this looks like 7 pixels. What if I say x divided by 100? Then we should see a repeating pattern every 700 pixels. But why is it so quantized? Why is this so quantized? That is because the resulting value of the sine wave is of course between 0 and 1. So we see as output, the left border is red. I don't know if you can see it. It's just a single pixel of red here. Then there's something in between. And, well, this is, I can't really tell. This must have something to do with the floating point nature of things. What if I just paste in sinus of 3? That's yellow. Okay. Sinus 2.5. That's also yellow. That's not good. So I think the issue that we're seeing is due to this sinus function, but I don't know what's wrong with it. Let's do a quick experiment. Let me just create a new file and let's call it experiment.c. And here we include standard.io.h, and below that we include math.h, and then we create a simple main method that outputs for I int I equals 0, I smaller than 100, or let's just do 20, I plus plus, so it outputs 20 computations of printf of a floating point number, and that floating point number is the sign of I. Okay, then let's compile output experiment, and as input we take experiment C, and it doesn't work. We have to specify that we're using the math library, so we do -lm here, and then it should work. So let me just execute it right away after compiling, and we have a list of values, and let's see if they make sense. So first of all, the first value is 0, then it's 0.8, then it's 0.9, then it's 1.4. I don't know. Maybe we have to smooth transition those values a bit. Let's do double, and then let's do sine divided by 20. So now we should have, and then let's multiply this with 2 times pi m pi multiplied with that. So we should have 20 steps of a full sine wave computed. Okay, pi is apparently not a constant. Is m pi a constant? I thought it was m pi. M pi seems to work. I don't know why my linter indicates that it's not. So we start with 0.3, blah, 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 1. Then we go down again. We go into negative space. We go down to -1. And then we go up again. So it seems as if the sinus function was behaving roughly correctly. I don't know why it didn't complete the entire loop. The entire, well, what is it called? The entire period. Okay, so let's go back to our main application. This is yellow. What if I do 2 multiplied by pi, which is a full period in pi, divided by width multiplied by x. This should give us a full period over the entire size of the display. But this is plain wrong. Maybe it makes a difference. Maybe, I don't know. Okay, it might be a problem that sine has to be between 0 and 360, of course, and it can't be negative, so we have to move it up by half the amplitude. Yeah, so we have a small sine wave, we amplify it by 360, and then we move it up 180. That should give us a sine wave between 0 and 360. What's that? I have the feeling that everything is correct, but something is not. And this is very, 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 very weird. The interesting point is, I studied electrical engineering and I did a lot of computations with sine and that kind of stuff. Why do I struggle with this point right now? It's ridiculous. So double sine returns a double. Let me just stupid check myself. Pi is 3.1415 or something like this. What's the issue here? Double I is 0, goes until I is 20. Okay, that looks fine. Oh, the values seem fine actually. So what's the difference with the colors here? Is there some wraparound somewhere? Is the RGB conversion wrong if I give it specific, very specific H values? That cannot be, actually. All the all the boundaries are correct. From 0 to 1, from 1 to 2, from 2 to 3, from 3 to 4, from 4 to 5, from 5 to 6. Does this step fail maybe, where we multiply those values with 255? We have an R plus R1 plus M value that should be between 0 and 1. If we multiply it with 255, that should work. What if I just make sure to cast this u int, well, int, no, I first have to multiply with 255, then I cast it to an int, and then that is cast into a uint8. Probably I can also directly cast into the uint8. I don't know. This looks still the same. I'm just doing guesswork right now. Int this. Int this. Does this look different now? Pink, black, pink, cyan. Let me undo all of this. Yes, this does now look differently. So this conversion here is the issue. Okay. But C convert double to byte. Well, let's first convert to an integer. Double A, int A. Okay, but how do we convert an integer to an unsigned integer? That might be a problem. Wait, are we... I don't want this to be an integer. I want this to be a uint8. What happens if I do this? Still the same thing. R1 plus M is a double value still. Then I multiply this with 255. I have to print those out. Print. What can I print here? Print H is a floating point number. Then R is a whatever digit. RGB and then HRGB. Let's see what happens if I now execute that. This doesn't work because I called print instead of printf. Okay, there's basically the answer. The H values smoothly transition, as you can see here, but then the R values and the G and B, somehow they just switch from 0 to 255. And that's why we see these distinct values. So they are either 0 or 255. There's nothing in between. Yeah, and that is an issue. Why is that the case? The R1 plus M, well, that can't be the reason. R1 plus M. What is R1? Let me just print R1, G1, and B1. They should be reasonable values, I would expect. They should be values between 0 and 1. And they are not. They are not. That is, of course, an issue. That means the R1, G1, B1 are faulty as well already. Why is that the case? They are doubles. Of course. I'm so stupid. That's what happens if you print floating point numbers as integers. So let's try again. But they still flip from 0 to 1. Okay, just for you to see, so R is 0.000, but G is 1.000. So there's nothing in between here. Why is that the case? Did I even input a good example here? Yes, we are generating different values of H here. Okay, so what is the issue? we instantiate doubles R1, G1, and B1, then we have those doubles up here, and they should all be floating point numbers. H is definitely a floating point number. Do we see different values in H? No, it's all 486, 746, 746, 746. Is there anything else here? Nope, it's all 746, so is maybe the input broken? Let me print F H here. H. I mean, that should result in something reasonable, no? Yeah, I think, I don't know why it's not black. It's trying to color something. C math use sign function. Let me just look that up. How it's properly used. We're doing exactly that. Use pi in sign function. We can use the value defined as m pi. Yeah, we're doing that. Is that all casts to a double? But I see that there are also a couple of other values for H here. Printing out all of those is horrible. Okay, so I will just assume that H is fine. I just lack something somewhere. HD is H divided by 60. That should also be a double. Something smells a bit burnt. I have to, oh God, I have to close the window. Okay, it's my neighbors barbecuing outside, wondering why I'm not invited. I could tell them so much about calculations in C and color spaces. Is this cast right here being applied before or after this multiplication? Because this is... No. Wait, what did we print out here? RGB, and they were R1, G1, B1, and they were values between 0. No, they are either 0 or 1 here. I don't get this. So it cannot be the casting. we are multiplying the values between 0 and 1 with the 255 first. Right? And only then are we casting. So now the parenthesis should be absolutely making sure that this is happening, but I mean, this shouldn't change anything. Let me just remove the printout statement for performance. Let me check for other ones. Well, let's just comment this out. Is there any other? No, there's none. And there's a missing semicolon in line 59. No, there's not. In line 54? Am I missing? Ah, I missed a closing parenthesis here. No, that was not it. Of course, because we also already determined that R1, G1, and B1 are somehow fixed to 0 and 1. Okay, guys, I just asked ChatGPT and it turns out that this right here, this absolute function is, wait, C apps is just for integers apparently. Where's some documentation about it? Oh, that's nice. I've never seen a formula on Google directly. So this is a big time saver here. So apparently we have to use F apps for floating point numbers, I think. So what's the difference between apps and F apps? F apps is type specific for floating point, etc., etc., and apps no, wait. There's difference between the one pulled from C standard lib and the one from C math. This is for C++. Math.h. Let's look up math.h. Math.h in C. What are the available functions? There should be apps. Yes, there it is. This is the issue. So we are using apps right now, which is defined. No, it's defined for doubles. In C, apps is only declared in standard lib. And so this is a detail for C++. So in C++, this is able to accept a double apparently and returns a double. In C, apps is only declared in standard lib and operates on int values. Oh my god, okay. So we have to get f apps, and where's that defined? It's in tg math, what? It's wait. C math f apps. It's part of the C standard library. Is it? Yeah, the fabs function takes a single argument in double and returns the absolute value of that number also in double. And that's why we saw those wraparounds, because that's the nature of the absolute function. Because if something wraps around and becomes negative, then something flips again, and then everything is horrible. So let's try. And I don't know, maybe we even entered undefined behavior here. All right. No, it's not it. Why? fabs comes from math.h. fabs of x returns a result. And down here we use abs as well. I almost gave up. I just really almost gave up. Let's try. And this is a rainbow-like pattern. It's still something is wrong, but here you can see a proper transition in the middle of it. So this is now getting closer to our goal. Are we using apps somewhere else? No, not here. So somewhere else we're messing up as well. Maybe there's an F sign function. I have no idea. No, it doesn't exist. What could it be? What could it be? H is a value from 360 to 0 to 360. So somehow we got closer to our goal, but still there's all this blackness in here and all this blue stuff in here, and there are a couple of rainbows in between. What is causing this weird pattern? I need a... Wait, what if I just do... Keeping it simple again, x, this should result in some fast pattern. Okay, that looks fine. That looks fine. Divided by double width. So now the width is cast to a double. Before it was probably an integer. That y is... Okay, it's using exactly half the screen size. Why is that? X divided by double width plus 180 degrees. Alright, maybe it's not exactly half the screen size. Yeah, it's not exactly. So it's not related to the screen size, I think. It's just at some point the function gives up and stops working. And that is because, I know. That is probably because h becomes negative after that. H becomes negative after that. Because we're using, no, that can't be, because we have moved the sine wave up by 180. I thought I have to put an fabs here, but that's not the case. We can just check. Yeah, still the same thing. So something is causing something magical to happen after we reach a certain point. But what is it? X starts at 0 and then increments from left to right, and then y is here. Do we maybe have to flip x and y? I think this makes no difference. No, this makes no difference. No, this can't make a difference. X is smaller than width, y is smaller than height. I'm already very happy with those rainbow-like patterns here. I just can't yet tell what is left to do. Let's scan everything from top to bottom. I am missing something. So we have now fixed the absolute function, fabs, and we have fixed the f modulo function here. Then we're checking if those values are in certain limits. It looks as if the loop was not complete somehow, but it definitely is. For example, if I print x and y after the loop, printf, then we should have the last coordinate in memory. Printf, x equals, and then it's a floating point number, so let's print that out. And y is also a floating point here. Maybe we shouldn't use core pixel values that are doubles. That's it. That must be it, guys. That must be it. We currently use doubles here, but we use them to construct even the rectangle for SDL. Maybe that is not really what we should do. Let me just check. I'm printing those things here. Let me just define them outside of the loop. Double x equals 0. Double x, y. Can we do this? I think we can't do this in C. And it doesn't even make sense in this case. So x, y are not defined. They are just declared here. Yeah, and at the end of the loop, they are 900. X is 900, y is 600. That's fine. Maybe the delay is too short. I don't know. Let's try again. Did they change something? What if I make it quite long? No, they didn't change anything. That would be surprising. Good. What if we do a 5 milliseconds delay? Yeah, doesn't change anything. So here we animate the surface. Maybe we can figure something out if we check from here, animate surface p window. Here we fill the rectangle black. Maybe that's not what we should do. Maybe we should do the classic SDL rect, delete rect, and that is an SDL rect. I don't think this is it. So I'm just desperately trying out stuff. X and Y are 0, and the width and height are screen width and height. And then we fill the rect using the delete rect, and we make it black. And then we define here the color black, and black is 0, 0, 0, 0, 0. So just like this. Doesn't work because we have to fill the rectangle using the address of the rectangle. Yeah, that doesn't change a thing as expected. I think we should have integers for looping over the pixels. And then for the calculation of the colors, we should use a double. But that's still the same result. But interestingly, at the end of both loops, x and y are 0. Why is that? Why is that? Ah, that is because they are now integers and I'm printing floating point numbers here. So now x is 900, y is 600. Have I somehow mixed up x and y? What if I just flip them here? Y and x. Desperateness. This is pure desperateness. That's obviously not it. And the solution is to... Please, solution, come to me. This can't be the end of me. This is ridiculous. 360 multiplied by this. What is the h value at the end? Let me also print that one. H. And that is a double H. Like this. So we have an H value of 482.71 something something at the end. How does this value come to be? This is not possible because we should have a sinus. The amplitude is too big of this. The amplitude should be, it's now 360. No, I miscalculated the sine wave. Wait. So normally a sine wave is defined on an xy plane like this. This is x, this is y, and then we have the value 1 and -1 here, and the sine wave goes from 0 to 1 to -1 to 1 to -1, etc. Not very precise. If I want to scale that, if I multiply it with 360, then it will go down to -360 to +360, and it will be this sine wave. Almost. I'm just trying to hit the 0 points here. And then I have to move it. No, this is way too much. I have to amplify it with half the amplitude. 180. And then move that up by 180. If that was the issue, then I'm going to freak out. I have no emotion left to freak out. Okay, very good. Next thing. What's the next thing to do? This is awesome. Now we can scale that sine wave to go through the full rainbow once. Okay, so we do sine x. So we have the double, let's call it okay, no, let's keep it simple. We have a double x and we have a double, and we have the twice m2, the 2 pi's here. And then we divide that with the double width, multiply with x, and that should give us a complete period of the rainbow. No, it's too much. It's too much. It's not properly scaled. 2 pi divided by width multiplied by the double x. How many periods do we have here? One starting here. That's weird. That's really weird. 2 pi Do I also have to double that? No. Two pi divided by the width multiplied with the double x. Something's wrong with that. Two pi multiplied by double x. Yeah, that's too small scoped. So we have to divide it with the double width. But that is somehow wrong. Why is this wrong? So x, double x, two pi are a full pi period. So we multiply that with 0 for the pixel x equals 0 and with 1 for the pixel x equals width. And then we start with the hue 180. That's the reason. That is the reason. Our first value is 180 if the entire sine wave turns out to be 0. How can I fix that? I mean, I just want to have, I think I want to have this instead. I want to have a maximum value of 360, and I can ensure that using the absolute function. I think this should give us the proper result. And it's still not what I expected. So here we have a positive loop over all colors, and then the inverse direction, because you can see red fades to pink again, even though it started from pink to red initially. So something is still wrong. What you're essentially seeing here, let me just pull up paint again, is, can we just scroll to some new area here? What you're seeing here is exactly this sine wave. So you're starting at red, which is 0, then it's growing to 360, then it's declining to 0 again. Here's another red bar, then it's minus 360. Screen doesn't allow me to go that deep. And then we're going up again. So I hope you get the point here. It's this that you're seeing. Okay, so basically it makes sense. It makes sense what we're seeing. I just don't, what I don't get is these lines, these black lines here, they don't make sense to me right now. And I don't want to have this full, wait, I don't want to have a full period. I want to have half a period because it's going to be in the absolute pi anyway, so that's sufficient. We just need one. No, we don't even need that. We just need half of a pi. Yes. And this is the spectrum that I was referring to. So now this is the part of the sine wave that is just, wait. What you're seeing now is just, let's say this is the sine wave. It starts at 0 and then grows the value until 360. That's what you're seeing. And after that, the sine wave would decrease again. So now we can play around with it, because now we have this function here and we can make it move. And that is what I actually wanted to do all of the entire time. So let's introduce a new variable here that is the timer. Or let's make it a double time. And time is passed into animate and is incremented. And if we go into the animate method and add time, which is a double, then we can add a time constant to this sine wave. And let's try. Let's see what happens. And we see this, and it's horrible. And that is because, very simple, we can't just increment it with 1 every time. That is way too big of an increment. We should do time plus, we should increment it with something very small, such as this probably. Or let's do it even smaller. Yeah, this is now a very, very slow animation. I will make it 10 times faster, in order of magnitude faster. And as you can see, we have a time constant, and that is shifting the color spectrum through the screen. Super nice, but it's a bit slow, and I think we can improve that here by just decreasing the delay. And now it's way faster. Super nice. Now, of course, that animation is quite boring, so let's augment it. Let's augment it a bit by adding another dimension. So right now our sine wave is just depending on x. What if we multiply the x with double y? Let's see what happens. And as you can, I need to interrupt this. As you can see, we now have this pattern, but it's moving on the screen. Ooh, this looks really trippy. This looks really nice, honestly. But this is a bit too fine-grained. What I actually wanted to do is something that doesn't deal with such huge values, such as x multiplied by y. But let's just put another component here. So let's call this hx. And then we compute another h, that is the y component, and that is the same, basically the same function, but with y as an input. And then we say that h is equal to hx multiplied by hy. So that basically is a multiplication of two sine functions. And I missed the semicolon here. Did I save? Double width plus time. All of that should be fine. Of course I have to say, or I have to declare hx and hy, and I can do that up here. Hx, hy. They are not meaningful in the color theory sense. They are just the components of x and y that determine the final h. Okay, as you can see, something's happening here. And that looks quite odd. Whoa, that looks nice. That's interesting. Did I mess anything up? I don't know. I generated the movie somehow. Looks like an intro to some blockbuster. Yeah, of course. We have to, of course, limit this. No, we have to change something. We have to calculate a plain simple sine wave here as the x component. Then we have to calculate a plain simple sine wave for the y component. And the result of both of those is now something between -1 and 1. So that's why it's red. Nothing's happening here. And then we can do 360 multiplied with that result, and then f abs. And let's see how that looks like. And now we can see a circular color spectrum. That is awesome. And this is exactly the thing I had in mind in the beginning. I would like to make this less fine-grained. This should not... We can just add a factor here. I want to have 4 such circles or such circle components on the screen. So let's multiply those by 4. And there they are. This is awesome. This is awesome. Let's just also look up, maybe what we have right now is a simple sine animation and they are moving. What would be interesting to see would be a standing wave. So let's see standing wave formula. It's sine multiplied by cosine. Can I just change one of them with cosine? Does that already generate a standing wave? I don't know. No. That just shifts one of the functions a bit, because sine is effectively the same as cosine. Of course, the arguments here are adapted somehow properly. Standing wave. What happens if I just change that to 40? What if I increment the time faster? Then I get this. Okay, this is basically waves traveling. But I want to have some nicer 2D function here. Let's look up standing wave. Yeah, standing wave would be quite nice, actually. But for that, I have to know the right wavelengths to combine. 2y max sine is 2 pi L divided by wavelength. And then cosine. Oh god. That would probably explode the scope of this video. So now we have this. Let me reduce that again. That looks nice. And then let's check what else we can do. Maybe we can do something like power of cosine to the power of 2. And maybe we can do the same for the sine. And remember, guys, this is pure C. So it's not just that we're generating some colors somewhere in some language. This is pure C, and this is awesome. Yeah, I think this is this enough for this video? I think we can stop at this point. All right, I will stop the video now. I hope you enjoyed this video. If you did, please leave a like as always. And see you next time. Exploring colors is actually quite fun. If you want to see more of this kind of stuff, then let me know in the comments. And I also appreciate your video ideas. If you want to have access to the source code, I will upload it to my private project repository. You can get access as a Patreon member. So if you want to support me, feel free to become a member there. See you next time. Bye.